Yesterday, we used your microbits as devices to collect data, to collect information from the world. We then manipulated that information, chiefly using if, then, else logic statements, which is a form of computation. Note that if, then logic statements are not the only form of computation. Yesterday, we also had a task where we converted degrees Celsius into degrees Fahrenheit, a calculation. That too is a form of computation. In fact, you can think of computation as everything from the information stage, the input into your microbit program, to the results when you print something on the screen. It's all computation. Over the next couple of days, I want to add automation into the mix. Automation being the ability of a computer to run a program many times over, perhaps without any human intervention, to achieve a result that would take us forever to try and do just as humans. To begin to illustrate automation, which is basically going to be a concept called loops in computer science, I want to use a classroom activity, one that I did as a student, one that you might have done as a student. It's close to my heart because it involves astronomy. And it's an activity where students map out the distances to planets. They make a model of our solar system using steps, their own steps as measurements. If you set one step as the Earth-Sun distance, what is called an astronomical unit, then, for example, Pluto is at 40 steps, and then the students can build a nice model of where the planets are. It's a nice task to do outside. So I want to introduce your microbits by turning them into measuring devices that count student steps. As with yesterday, in terms of the Wyoming domains, this session will cover devices. It will also cover aspects of algorithms and programming. Specifically, we're going to introduce variables, and we're going to touch again on control.
Today's tutorial is going to focus on automation. We're still going to have information that is input into your microbit, and we're still going to perform some computation, but we're going to introduce the concept of automation, make the device do something over and over again. The goal is to be able to use this in a real-world example, and I sketched out the idea of a student being able to count their steps to map out the distances to planets in our solar system. When you think about automating a problem in computer science, you're going to start to think about loops. Loops tell a computer program to do things multiple times. So for example, you may not have found it, but in the last tutorial, I included a task where you could print something to screen, show something on the screen multiple times, and that would have required this loop. There were other ways to do it. But you may not just want to execute something 1, 2, 3, 4 in this case times. You may want to execute it forever. If some logic condition is met, you may want to just do things again and again and again, and that would be this loop. Those are the two main examples of loops. So let's consider a simple example of automation. Another concept I'm going to have to introduce that we didn't use yesterday is a variable. When I loop over something, when I do something multiple times, a lot of the time I'm going to be doing something to a specific item, to a specific thing. And this is a variable. So in this case, I've created a variable already, and I've called it counter. And some things you can do to a variable is you can use this as a pure math input to your problem, something that doesn't necessarily come from the outside world. So you can set the counter to some number. You can change your counter by some number. You could also use a variable for an item from the outside world, something that was sensed externally, and make that your variable. So for instance, you could take the temperature. If the microbit senses that the temperature is 21 degrees Celsius, you could put that in a variable. You can make a variable called, for instance, temperature or temp. And then you could store the temperature in that variable and then do something with it. But let's use my variable counter to illustrate in its simplest form information. So initially, I'm going to set my counter to some number. I've just used the default here, 0. And to automate something that happens to that counter, I'm going to have to say, okay, while some condition is met, we're going to do something to this variable, to this counter. And the condition I'm going to use, the logic condition, is simply all times, while true. And something is always true, true is true, while true will do something for all times. I'm going to do something to my counter. I'm going to increment it. And then we have our inputs. I'm going to do it on start, and we have a result here. I'm going to show the number counter on the screen, show this variable. So let's put all this together in blocks. When the Microsoft microbit starts, if something is true, and it is the case that something is true, while true, so this will just run because true is always the case. I could, as we did yesterday, put a logic condition in here. So I could go over here and instead of while true, I could have while x is greater than 7, while the temperature is less than 4 degrees Celsius, while the light level is a certain amount, or while the light level and the compass heading are certain things. But let's just always execute this. So while true, you can think of this as, if you like, while the temperature is greater than minus 400, which is always going to be the case, so while that's true. When we start the program, I want my counter to be 0. And then for all time, while true, I'm going to change my counter. I'm going to increment it by 1. And then we want to see what's happening, so I'm going to show my counter to the screen. So let's see the result. You can see that we started at 0 and we're just counting up. And because it's the case that that true is always true, while true, this will just keep counting forever and ever and ever. You see it's got to 13, it's got to 14, it's just going to keep going up. If I'd started with my counter at another number, so let's set the counter to 19, then when we started the program, it would have started counting up from 19. And because while true is always the case, it's just going to keep counting and counting and counting. So you can think of this as automation. The microbit, we could put it in a cupboard somewhere if it didn't run out of power and come back 100 years later and it would still be counting. You as a human being wouldn't want to automate this process. You wouldn't want to keep counting upwards and upwards and upwards for 10 years. But the microbit will happily do it. Computers are very good at automation. Notice we still have a computation here as well. It's not an if-then computation, but it is some math in here. I changed my counter by 1. So I'm combining automation and some computation from my information, which was my initial 19 that the counter was set at, and I have some result, and I just need to display that result. So we're showing the number. Now on to today's task. What I want you to do is make a counter that students could use such that whenever the microbit is shaken, the student will count 1 step. So the idea is, as a student is measuring out a distance by stepping, each time they take a step, they will shake the microbit and the counter will increment by 1. So that's the simple goal. Just program your microbit so that when it is shaken, to screen, the number of steps that have been taken are printed. You're going to need, like we did yesterday, some logic loop that says if something is true, and you're going to need from the inputs, the thing that you want to be true is if the device, if the device is shaken, on shake. So try and put that together to make a counter that every time a student shakes the device, it displays the next number. Some stretch goals for this project. If you like, try and tie it back to my idea of the model of the solar system and students taking a step. I've looked up the numbers on Wikipedia, how far each planet is in terms of steps. And if we use the Earth-Sun distance, which is called an astronomical unit, then the Earth would be 1 step from the Sun. Jupiter would be 5 steps. Saturn would be 9 steps, and Pluto would be 40 steps. I'd like you as a stretch goal to, when the counter reaches that number of steps, in other words, if the student has taken that number of steps, display the planet name. So for instance, if a student has taken 5 steps, display Jupiter on the microbit screen. If the student has taken 9 steps, print Saturn to the screen, and if the student has taken 40 steps, display the word Pluto on the microbit screen. Finally, if you get through all of that, which you may not, an additional stretch goal is to only show the number of steps that the student is taken if button A is pressed. It turns out that in this model of the solar system, 1 step corresponds to 93 million miles, roughly the distance from the Earth to the Sun. So just as if the student presses button A in this stretch goal, you would display the number of steps, and only if the student presses the button, not display them constantly. If the student presses button B, display not number of steps, but number of 93 million mile increments. So 1 step would be 93 million miles, 2 steps would be 2 times 93 million miles. So the most important thing is to program the microbit so that when it's shaken, it displays the next number of steps so the student can have a device for measuring how many steps they've taken. But try those stretch goals as well of printing, say, Jupiter to the screen when the student's taken 5 steps, and also of only displaying the number of steps when the student presses button A, and displaying the number of 93 million miles corresponding to 1 step when the student presses B. And I'll come back at the end with a solution and we'll see how you've done.